O tym, że redukcja emisji w rolnictwie zaczyna się już dzisiaj. O tym porozmawiamy teraz i nie ma absolutnie na co czekać. Przed Państwem Panuncio Moscoso-Jara, International Scientist, Sustainability Strategic Research.
Hi, so my name is Panuncio and I'm part of Yara. I'm a strategic researcher in Yara's R&D center in Hanninghof, Germany. And today we are going to talk a little bit about how crop nutrition can contribute to reduce greenhouse gas emissions. And to start with some facts, we all know about this. Global population is increasing and the production of more food becomes more challenging. And basically, if we need to produce more food, one of the biggest global challenges is to actually produce more food, but at the same time to reduce greenhouse gas emissions. And if we need to do so, we have two options. One is either we increase the productivity in the area that is now under production, or either we expand agricultural land. The problem, or one of the many problems with expanding agricultural land, is that changes in the land use, it's a major contribution to greenhouse gas emissions. So we know we need to produce more, and we need to do it in the area that is now under production. So what we need to do is to increase productivity. And only to review the basics of crop nutrition, there are minerals are essential building blocks for biomass production. They are essential nutrients, and this means from a plant nutrition point of view that those nutrients must be present for the plant to be able to complete its life cycle, and its metabolic role cannot be replaced by any other chemical element. So we know that we need to produce biomass, we need nutrients. But we also know that if we want to produce more biomass, we need more nutrients. And here we see how an increasing yield in two crops, winter wheat and potato, it's related to an increasing nutrient uptake. And the thing is that when we repeatedly extract nutrients from the field with the harvest, we deplete soil capacity to provide nutrients, and this eventually leads to soil degradation and, of course, reduced yields, increasing the pressure of a land use change. And this means then that because we need to produce more, we can just use fertilizers indiscriminately in order to achieve our goal. And of course, the answer to that question is no. And here is where I would like to bring into a discussion how we understand regenerative agriculture and what regenerative agriculture actually is for Yara. And we all know that there's not a common global understanding of what exactly it means, but there are a lot of themes that are recurrent in all the definitions. So Yara has defined regenerative agriculture as an outcome-based approach to adopt the best sustainable farming practices that have a positive impact over nature across 5 themes: climate, soil health, resource use, biodiversity, and prosperity. In today's presentation, we are going to focus on the first pillar and climate, and to see if we can try to achieve our goal of mitigating greenhouse gas emissions. And if we want to mitigate something, first we need to understand the system. And we are going to base this presentation in potato crop. And as you can see, agriculture currently accounts to around 20% of global gas emissions. And as we just discussed before, if you see the light blue line, that represents changes in land use. And that's basically half of the emissions coming from agriculture. That's why it's absolutely necessary to avoid expanding agricultural land as much as possible. But if we see other components, we also see that both fertilizer use and fertilizer production are significant contributors. And if we go deeper into potato crop, we made a literature review of life cycle assessment because we wanted to understand which are the major contributors of emissions to that system, or where the hotspots were. And we see that farming across the food chain has a significant share. And if we break down farming, we find out that both fertilizer production and fertilizer use in the field are major contributors. So then there's something we need to take care of here. And this is very interesting to see because it's a case study in the same year, in the same area. This happened in Argentina. Those are all different farmers. Potatoes were grown in exactly the same environment, so there were no difference in that matter. What is the difference between all these farmers? Everything else. So management was different, even varieties they used were different in some cases. If they irrigated, the irrigation system, the energy used in the irrigation, the amount, the source of fertilizer, the rate of fertilizer, the crop protection, everything was different. And we can see there the massive difference that we find for these different farmers in relation to the emissions of their crop protection. And even if we see for the same variety, we see that there's a lot of variability. So that gives us a lot of room for improvement. And it's already telling us that our management practices have a lot to do with the emissions. And we are going to focus then on those two hot spots, the fertilizer production and the use of fertilizers in the field a little bit. And when we talk about fertilizer production, we talk about the emissions that are associated with the production of that fertilizers at factory gate. So the square that it's there in the drawing. And why does that matter? Because it's very different. This was a publication done by Bentrup, and we can see there that for the same fertilizer, in this case it's ammonium nitrate, there is a lot of difference in the product carbon footprint for that fertilizer. And that's related to the energy used and the technology used in the production of that fertilizers. So technology used in the fertilizer production absolutely matters, and it makes a difference. And we need to know where the fertilizers we are using are sourced from, with which technology they are produced. And when we talk about technologies of the fertilizer production, what exactly are we talking about? So there are different greenhouse gases that are produced and emitted to the environment during the fertilizer production. One is N2O, another one is CO2. In the first column, what we are seeing is a nitrate-based fertilizer that is produced using natural gas as a source of hydrogen for the Haber-Bosch process and energy. And if we go to the second column, there's already technology applied to the production of that fertilizer, and we have an N2O abatement system. Those fertilizers, exactly the same fertilizers as the ones before, only because they were produced with a different technology layer, can already achieve between a 50 to 60% reduction on their production side. There are different types of technologies also related. If we go to the next column, we see what we call carbon capture and storage. And it's the same fertilizer, but still produced with natural gas, also using the N2O abatement technology, but the CO2 that is produced in the production phase is captured and stored safely and permanently under the North Seabed. And there are another type of fertilizers. There are the ones that no longer rely on natural gas, but they mainly use hydrolysis of water as a source of hydrogen, powered by renewable energy, or use renewable natural gas. And with these fertilizers at factory gate, we can already achieve a 95% reduction on the fertilizer carbon footprint at factory gate. That's really significant. And if we see how this is translated into a real crop case study, this is a potato crop, a non-irrigated one in Germany. So if you see the green part and the gray part are exactly the same. We are not changing any management practices here at field level. The same rate of N applied, the same source of N, in this case it was CN. The only thing that changes is the blue part. That is the one related to the production of the fertilizer that we are using. And only by changing that, we can already achieve, in this case, up to a 40% reduction in the crop carbon footprint without changing anything else in our management practices. So that really, it makes a difference. It's really important. And then the other part is related, okay, fair enough, fertilizer technology matters, but then it also matters how we manage that at the field level. What do we do with that? And here, Every decision counts. Everything that we are doing has an impact. And it's all about knowledge applied to the field. It's easy to say, but it's really difficult to put together a sustainable crop nutrition program. It takes a lot of knowledge of the soil, of the farm, of the crop in order to put together that. And we can rely in helping us how to achieve that in the 4R concept. When we talk about the 4R, we talk about the right rate, the right source, the right timing, and the right place. We don't have time now to go deeper into this, but the 4R concept is going to help us achieve our crop production goals, but at the same time, minimize as much as possible any losses from the system and maximize crop uptake. That's our goal, to reduce greenhouse gas emissions. And one of the ways that we can measure how good our 4R management practices were, it's using a key metric indicator as the nitrogen use efficiency. And why nitrogen use efficiency matters? Because you can see here how nitrogen use efficiency is related to the Sustainable Development Goal. And it's really clear to see that if we apply too little nitrogen, we have a problem. Why? Because we are still farming, we want to achieve as much as possible yield, but it endangers food security because yields are going to decrease. It promotes soil degradation, and it again puts pressure over land use change. That's not something that we are looking. But on the other side, if we apply too much nitrogen, we also have a problem, a very big problem, because it's not sustainable either from an economic or an environmental point of view. And here we have end losses to the system, reactive forms of nitrogen being released and greenhouse gas emissions increasing, water pollution, and so on. And the EU Nitrogen Expert Panel developed what they call a safe corridor for nitrogen use efficiency. So this helps us understand and evaluate how our management practices are. And what they say is that when your results of nitrogen use efficiency are below 75%, there's too much risk for end losses. So the nitrogen that we are putting into the system, the crop is not uptaking, and we are creating a lot of problems. But on the other hand, if our nitrogen use efficiency is very high, again, we have problems because we are taking from the field much more than what we are applying. And on the long term, this has a really big effect. And you can see there 3 different points, and those represent treatment from a trial that we have in Hanninghof that it's running for 65 years now. And the different treatments in this trial is lacking one or the other nutrient. And there's a treatment with no nutrients at all and a treatment with balanced nutrition. Here I only put 3 dots not to make crowded, but as you can see, the only treatment that it's in the safe corridor is the one with balanced nutrition, telling us that nitrogen alone does not do the deal. All 3 treatments receive the same source of nitrogen and the same rate of nitrogen. But if we are lacking any other nutrient, then we are not able to use that nitrogen efficiently. So to sum up, the key actions to reduce greenhouse gas emissions from crop production is to use fertilizers with lower carbon footprint. It's very important to know where the fertilizer we are using is coming from and the technology which that fertilizer was produced. It really matters. Also, to use that nitrogen efficiently at field level, and we need to reduce as much as possible end losses from the system. Every kilo of nitrogen that we are putting in the system matters, and we need to be sure to use it efficiently. And of course, to increase productivity on existing farmland to avoid as much as possible the conversion of natural land into cropland and the greenhouse gas emissions associated with that. Thank you very much.